Good evening, everyone. Welcome to the session.
Good
Good
evening.
evening, sir.
Good evening, sir.
Yes, welcome back. So we'll wait for a few more to join and then we'll begin the session. So any doubts if you have, yes, you're free to ask. We'll discuss them. So meantime, let others also join. So any doubts, Shweta, Akshaya?
No, sir.
No, sir.
Okay. Yes, you're Priya. Hope you've gone through the first lecture.
Yes, sir.
Oh, easy to follow.
Yes, sir.
Okay. You got already habituated, right?
Yes, sir.
Okay. Yes, Mageshwaran and Yogesh Raj, welcome. Welcome to the session. You can, yes, if possible, you can connect your mic as well. Yogesh Raj, please confirm the audibility and the video is also very clear from your end. Yogesh? Okay. Yes, Yogesh. Is it clearly audible?
Yes, sir. It's audible.
Okay. How about the video? Clear?
Yes, sir.
Okay. Then. Yes. Sir. Any doubts? You're free to interrupt just by unmuting your mic and then you can speak whenever you get a doubt like physical class. Okay.
Okay, sir.
So other than that time, you can keep the mic in muted condition. Anyway, it is in your control. When you are speaking, you can unmute and speak. Mageshwaran, if possible, you can connect your mic as well so that you can have a good voice interaction whenever you get it out. Okay, yes. So we'll begin the session. Okay, so I have just introduced two important switches, essential switches. With them only we can build entire logic families. That means logic gate family. Okay. You got a glimpse of a logic gate, that is a NOT gate using PMOS and NMOS. So let me in detail talk about this switching transistors. Okay, so we'll introduce NMOS and PMOS. So here they serve as only switching transistors, switching element. They serve as only switching element. They are transistors fundamentally. They are MOSFET transistors. Enhancement mode, metal oxide semiconductor field effect transistors. Anyway, MOSFET itself is having a T, that T refers only the transistor. Okay. So MOSFETs, NMOS and PMOS are going to serve as only switches now. Okay. Right. So NMOS, they are complementary switches. Okay, they are complementary switches. So depending on what they demand to turn on, NMOS demands something to turn on, PMOS demands something to turn on. Okay, so there, and those who attended analog electronics will have a good idea about, okay, so when NMOS will turn on, when PMOS will turn on. Okay, but here we are not getting into analog. Here we wanted to know just how they act as switches. That's all. Okay, so they are simply switching elements. So we are replacing switches in the switching logic theory by this NMOS and PMOS transistors. So first let me introduce NMOS. So what is NMOS? Okay, so it's a digital introduction about NMOS. NMOS is fundamentally an active high switch. Active high switch. That means when the control input, which is controlling the NMOS operation, if that is high, it is going to get closed. Okay, going to act as a closed switch between the two terminals. So what is a switch? Already I said the switch is nothing but switch should have two terminals, the top and bottom terminal, and then the switch should have a control mechanism. That's what we demand actually. We have a switch, That switch can be in open state or closed state, but it should be controlled by a signal. It should be controlled by a signal. So we need actually 3 terminals. Okay. So this is switch terminal 1 and this is switch terminal 2 and this is actually the control terminal. That's your perception about your NMOS. So I'm giving the digital logic symbol of NMOS. This is your NMOS. That is your terminal 1. It's also belong. That is your switching terminal 1. So switch is placed between the top and bottom terminal. Okay, you are visualizing NMOS like a switch. That's all. The control is whatever the input you are giving to the gate terminal of your NMOS. So with respect to NMOS, we are not getting into the current versus voltage characteristics, only the switching characteristics. That's all. So this terminal, we call it as a drain. This terminal, we call it as a source. Okay, in analog circuit, we refer this arrow. That arrow we don't prefer in digital. Okay, so how we are going to distinguish PMOS, we'll see. So without bubble at the gate represents active high switch. Okay, so that is getting enabled when the control input is logic 1. Okay, that is called active high. That means the element is active when you give high input. That's what it means. That is your gate terminal. Okay, that's your gate terminal. Shortly we denote it by G. This is denoted by drain and this is denoted by what? Source. So the switch is between drain and source. That switch, okay, ideally getting closed means the voltage across the switch is equal to 0. That's ideal case. The voltage across this is equal to 0 volt. Okay, because it's a switch. What is the voltage across? If it is closed, what is the voltage across a closed switch? What is the even contact resistance of the switch can be treated as a 0. So there may be some current through the switch, but there is no drop. The voltage across the switch is taken as 0. So whenever a switch is closed condition, the voltage across the switch is equal to 0. So treat this voltage between drain and source 0 the moment the switch is in on condition. That's what it means. And that is enabled by the gate signal. So gate signal is nothing but your digital logic signal that is going to be either logic 1 or 0 only. The gate is activated by a digital logic signal that is either 1 or 0. 1 means it is actually 5 volt analog 5 and 0 means it is analog 0 volt. Getting? All of you getting? So if you give for NMOS, those who already attended FET amplifiers, okay, so already know the basics of FET. So if I give 0 volt, will the FET NMOS will be in on condition. If I give 0 volt to the gate terminal, that is VGS. You have to feel like VGS, okay. So gate terminal 0, VGS equal to 0 means will it be on condition?
No, sir.
Okay, yes. Okay, so that is 0.5 volt. Definitely it is more than the threshold voltage. Definitely the NMOS will be in on condition. Correct? Yes or no?
Yes, sir.
Okay, so hope you remember something, but we are not exactly exploiting all those fundamentals here. So as of digital logic design is concerned, we are using NMOS and PMOS only as switching elements. So if the input control input is logic 1, it is on. Control input is logic 0, it is off. That's what it means. So that means when the gate terminal is activated by a digital logic value 1, it is in on condition. So the gate terminal, let me call this is excited by, let me take it to the next slide. So this is my NMOS digital logic symbol. Switch terminal 1, switch terminal 2, and this is the control terminal. So this is excited by a Boolean, okay, variable A. And this A will have a digital value 1 or 0. Okay. So now this is your NMOS. State of NMOS depending on your A. So it's state of NMOS. Here NMOS as a switch. NMOS as a switch only. Okay, yes. Yesterday itself I have given glimpse of this state of operation of NMOS. So A is equal to 0. Since it is active high switch, it is looking for A is control input logic 1. So since it is 0, NMOS remains in off state. Off state. Okay, yes. Then A is equal to 1. The control input is 1. It is looking for active high logic. It is 1 means it is going to be in on state. Okay, so NMOS as a switch It is off when A is 0. It is on when A is equal to 1. Okay. It is just complementary when it comes to PMOS. Okay. So PMOS is also acting as a switching element. So similar to this, when it comes to PMOS, consider a bubble. It's not analog symbol, it's a digital symbol. Okay. With bubble, it's PMOS. Without bubble, it's NMOS. Don't look for the direction given earlier in analog symbol. For a source, I have given an arrow. That arrow I am not using in digital. So this is a digital logic symbol of NMOS and PMOS. So this is your PMOS. The moment you see the bubble, you have to feel like it's a active low switch. It's a switch, but it is looking for active lows. It's active when you give the control input as low. Okay, so the switch is called as active low switch. PMOS is active low switch. Okay, like how I introduced NMOS earlier. What is that? NMOS is fundamentally active high switch, and this is active low switch. PMOS is active low switch. Okay, but strictly the application of PMOS is limited to pass only strong logic 1. It is a good strong passer of logic 1, passes strong ones. But if you connect it to pass logic 0 to the output, then it is passing, actually it passes a weak 0. It is going to pass a weak 0. Weak 0 means always we are looking for strong 0. We are looking for strong 1. We should say strongly it is 1 or 0. There should not be the signal we are getting in the digital logic design output. It should not be in a dilemma. Okay, so the voltage level, for example, 0 is 0 volt means 1 is nothing but 5 volt means now I'm asking you 2.5 volt belong to what logic level? Can you say 0.5 as a logic level? Can you?
Yes, sir.
Yes, the 2.5, that's definitely is going to put us in a dilemma. So that means it's neither strong 1, it's neither a strong 0. So the circuit will be in dilemma. The circuit which is going to sense this 2.5 volt will be in dilemma that whether it is received logic 0 or logic 1. So it won't take a proper function. It won't work properly by seeing this signal. Okay, so therefore strong 0 means exactly 0. Strong 1 means exactly 5. That's all the digital logic is all about. Okay, so in between something, but there is a margin. Okay, so 0 means how long it is margin. 0 means maybe 0 to 1 volt treated as 0. Maybe 4 to 5 volt, okay, will be treated as logic 1. Like that, there is a margin available for low logic and high logic. So this is called 0, low logic margin. 0 to 1 can be treated as low logic margin. 4 to 5 can be treated as a high logic margin. There are certain margins. So beyond this margins, okay, like 2.5 is neither belong to logic 0 nor belong to what logic 1. So the circuit which is sensing 2.5 volt won't understand what the previous circuit is, what the previous logic gate is giving as an input to the next stage. So it won't take a proper decision and won't give a reliable digital logic output. So therefore we should never put any digital logic design in a dilemma. So we should convey strongly whether the input is strong 0 or strong 1. Therefore we should use switching elements in such a way that they are capable of passing only strong logic levels, and no switching element should pass weak logic levels. Okay, so therefore the benefit of PMOS is it is a very strong passer of logic 1. That means it's a very good passer of logic 1, strong 1. And but it's a, if you're asking PMOS to pass logic 0, it will pass only weak 0. So that means, so it's a switch. So either you can use this PMOS switch, this is for pull up and this is for pull down, because I said already we are going to use two switches either for pull up purpose or pull down purpose. Suppose if you are using PMOS switch for pull up, yes, it is happily going to pass a strong 1 to the output logic, output variable. Okay, suppose instead of using PMOS for pull up purpose, suppose intentionally if you are trying to use PMOS for the pull down purpose, yes, it is not going to, because what is pull down? It is going to pull your output to logic 0. So that is going to pass only a weak 0. Never do that. That means never use PMOS for pull down purpose. Getting everyone? Yes or no?
Yes, sir.
So PMOS always for, PMOS switches always for
Pull up.
network. Never use PMOS for pull down purpose. If you use it, yes, it will pass a 0, but it is a weak 0 only. So the next circuit will be in a dilemma. Okay, it won't understand whether it is surely 0 or not. It won't be a strong one. Okay, and similarly, okay, when it comes to NMOS, NMOS is a strong passer of 0. That means passes a strong 0. Therefore, one can happily use it for pull down network. So it is capable of passing a strong 0. But when you connect it for pull up purpose, NMOS in the top is pull up, bottom is pull down. So when you use it in the top, NMOS for the pull up network, then it is capable of passing, but it is going to pass a weak one. It is going to pass a weak one. Okay. Getting? So when you use it for pull up network, that means never use NMOS for what? Never use NMOS for what?
Pull up network.
Pull up
Pull
network.
up.
Always NMOS finds application in pull down only. So that means the pull down network is completely function of NMOS switches. The pull up network is completely function of PMOS switches. That's all. So therefore, it's mandatory to use CMOS switches in any logic gate realization. In any logic gate realization, it is mandatory to use CMOS switches. We shortly call them as CMOS switch. What is one CMOS switch? One CMOS switch will have what? One NMOS and one PMOS. So that is what we call as complementary MOS transistors, because NMOS and PMOS are complementary to each other, because this is active high enabled and this is what? Active low enable, and this is capable of passing what? Strong 0, and this is capable of passing what? Strong 1. Easy. All of you getting? Yes.
Yes, sir.
So because of this only, first we go by switching logic theory. So then we wanted two switches. Okay, so we wanted two switches. Yes, you can happily go by no resistor, no more resistor, because resistor is a power dissipating element. Okay, not the switch. Okay, so there is no power loss across a switch, ideal switch, but there is a power loss across resistor. That's why never use resistors, because in digital logic design, even gates also should consume less power only, logic gates also. So then we have the control, that's a pull up switch, and we have a pull down switch. The control is given by, yes, the signal A. Okay, this is your signal A. A is the one going to control it, and that is the one going to produce your output Y. Okay, this is your logic high, that is 1, and this is logic low, that is 0. Yes, now. Okay, this is a control only, control terminal of your switch. Okay, yes. Fine. So what is happening here? So these are the complementary switches. Complementary switches. That means what? This is the switch S down and this is the switch S up. That means this is A. That's what we demand. Okay, SD, SU and Y. Okay, so we have done it yesterday. Once again, just completing the formality. So A is equal to 0. The down switch is what? Closed. 1 minute. A is equal to 0. Down switch must be
0.
1 minute.
Opens.
1 minute. Stay online. A is equal to 0. The down switch is open, and up switch must be closed.
Closed.
Then Y is equal to logic 1. That's expectation. Okay, complementary switches. So bottom switch is open and the top switch is closed. That means the Y must be either pull down to logic 0 or pull up to logic 1. Okay, so that's why it's a complementary requirement. So both are sensing A, but one should be open, another one should be closed. That's why yes, you must be demanding a PMOS. Because PMOS demanding, it's active low switch. If you give okay a low signal here, so A is equal to 0 means this is getting 0, this is getting 0, but this is open, but this is getting closed. So therefore Y will be pulled to logic high. Okay, then A is equal to 1 makes your second, that is a bottom switch, active high switch. So this is active high switch and this is active low switch. Okay, that's easy now. Active low switch looking for logic 0, active high switch looking for active, there is a logic 1, therefore it is 1 means it is closed. Bottom switch is active high switch, it is getting closed, whereas the top switch which is
Open.
active low looking for logic 1, but actually you're giving logic looking for logic 0, but you are feeding only what, logic 1, so it is going to get what, open. Getting everyone? Yes, because of this now Y is now pulled down to logic low, that is equal to 0. This is what we call as the basic inverter logic. That's a switching logic theory only. We call it as inverter logic or not logic using switching logic theory. Easy everyone? Yes.
Sir.
Okay, shortly we call it as Y is equal to complement of A. Y is equal to complement of A. Then we replace this, which is okay, based on this understanding, we replace this by a PMOS and we replace this by what? NMOS. They are the real switches. Okay, controlled by the gate signal. Okay, so gate is driven by gate of PMOS, NMOS will be tied together and enabled by a logical signal A, digital logic signal A, and that is going to produce a digital logic signal output Y. Okay, so because of this only we are getting the famous digital inverter or NOT gate structure using one CMOS like this. Sometimes it may be given as VCC or VDD. Okay, that's your logic high. So here we have your PMOS with a bubble. Sometimes they will confuse you by giving arrow as well. Okay, never get confused. Then without bubble, that's your NMOS. With bubble, active low in digital from now itself. With bubble, active low. Without bubble, active high. Feel that way. Okay, that's a ground. Then these two are tied together. That's a perfect CMOS inverter. Driven by input, that is logic A, signal A, input signal A, output signal Y. Yes, that's all. So this is your logic 1 or high, this is your logic 0 or low. Okay, so you have NMOS, PMOS. This is what given yesterday. A, state of NMOS, state of PMOS, and then your Y. A is 0, NMOS is off, PMOS is on, Y is connected to logic 1. Correct? Correct? Because it is active high switch and this is active low switch. Both are controlled by the same input. So PMOS looking for active low. As A is low, it is enabled. And it is 1, NMOS goes on, whereas PMOS pulled off. Therefore, output is pulled down to logic 0. Then again, Y is equal to A bar. So this is equivalent of what? A simple inverter logic. Yes. What is the cost of this NOT gate? Giving A as an input, getting output as complement of A. Yes. That's your NOT logic. Yes. What is the cost of this NOT gate? Now you know the cost. You know the budget of your digital logic design. Yes. What is the budget?
1 CMOS.
1 CMOS is the budget of inverter gate. Okay, NOT gate. NOT gate demands 1 PMOS and 1 NMOS. A simple 1 mark problem. Okay. 1 mark question. Okay, in the gate level. Any doubts in this? So the first logic gate one has to implement to understand digital logic design is CMOS inverter. Okay, so digital logic design ideally begins with the design of CMOS inverter. Okay, so not to the back end, even in the front end level. Okay, hope it is clear. Anyone having doubts in this? Yes, Maheshwaran, able to follow?
Yes, sir. So I just have one doubt in the previous slide, sir.
Yes,
So
Maheshwaran.
initially we are just taking active low and active high switch, and later on basic on the depending on the behavior, we are naming it as PMOS and
Yes,
NMOS switch, right, sir?
yes, exactly.
Okay, okay, sir.
Okay,
So the combination.
we are demanding the pull-up switch as a active low switch and pull-down switch as active high switch.
Okay, sir. So this two combination provides us the CMOS switch, right?
Yes, active low switch is our PMOS, active high switch is our NMOS.
Okay, sir.
Okay,
Now,
so first I'm going by switching logic theory, then I'm replacing switches by the practical transistors. Okay,
okay, sir.
so this is the practical design. This is only theory. It's only in papers. Then what makes the reality means only your PMOS and NMOS makes the logic gate realistic. Okay.
Okay, sir. Now got it.
So ultimately the goal is we wanted to realize a logical function Y is complement of your digital logic A. That's all. Okay. Ultimately the goal is we wanted to implement a logic function called Y is output is a complement of your input. If input is 0, output should be 1. If input is 1, output should be 0. That's a demand. Okay.
Okay, sir.
And by default, we made some important conclusion. PMOS always acting as a pull-up network and NMOS always acting as what?
Pull down.
Pull-down network. Yes. Okay, that's very important. So never make pull-up using NMOS. Never make pull-down using PMOS. Okay, because NMOS is a strong power of 0. PMOS is a strong power of logic 1. Okay, so they are playing the role to their best. Okay. Yes, Yogesh Raj, able to understand?
Yes, sir.
Okay, any doubts?
No, sir.
Okay, so next. You tell me what logic gate is implemented by using this setup. A CMOS logic circuit is given, what logic function it is implementing. The top is logic 1 or VCC. One can say VDD also, okay, because the moment it is a FET, we use VDD and the bottom as the ground. VDD is logic high, top rail, and this is the bottom rail logic low. Yes. Now let me connect the, I'm going to use 4 switches now. Strictly PMOS for the pull-up. Output Y, A, B, A, B. A 2 CMOS design. I'm making a 2 CMOS design. So tell me what is Y as a function of A and B. Give me the Boolean logic expression for the output signal Y. Digital logic output signal Y. Let me keep it as it is. We'll have a copy of the same, then we'll do the analysis. Call it as P1, P mass 1, P mass 2, N mass 1, N mass 2. Okay. So we'll have a table A, B, N1, N2, P1, P2, Y. That's easy. A and B will have these other two input signals. How many combinations possible between A and B? How many combinations possible?
4 combinations.
4 combinations. 0, 0, 0, 1,
0, 1.
1, 0, 1, 1. So we'll see what the table is. It is going to speak some truth about what is happening in this. So we'll call this as a truth table. So by the time you complete the truth table, we can establish a good connection between Y and the digital logic input signals A and B. Now 0, 0 I am giving. So tell me what is state of N masses, N1, N2. N1, N2 are active high switches. So if you give 0, 0, both are in what condition?
Off.
Off condition. So off, I'm using off state of the switch, I'm using 0. On state of the switches, I'm using 1. Okay, yes. So both the NMOS are off condition means they are open circuit. Open circuit means Y cannot be connected to digital logic 0, correct? Yes or no?
Yes, sir.
So when both the NMOSs N1 and N2 are open circuit, Y cannot be pulled down to 0. If Y cannot be pulled down to 0, what else can be the state of Y?
1. Pull up.
1.
Yes, it has to be. Then who has to offer a path? One who has to offer high logic,
PMOS.
one has to pass. So when no path is offered by N1, N2, there must be a path from high to Y, and who is going to offer that path? Both P1 and P2 will
P1.
offer that path because they are in on condition, correct? Yes or no? All of you getting?
Yes, sir.
So since active low logic switches they are, and both A and B are 0, 0. So P1, P2, both are in on condition. Therefore, they will happily connect, both will connect logic 1 to output Y. So output is logic 1. Easy. Yes, you can, the moment you are getting some answer from the pull down network, then automatically you know, because Y is always going to be either a strong 1 or strong 0. That's how you need to connect your pull down network and pull up network. It's very important. I already made such a design. 1 minute, I'm committing a mistake. Pull up network, and this is pull down network. Okay. So when pull down network is not connecting Y to logic 0, and automatically the pull up network has to connect Y to logic 1. That's a mandatory condition when you are building logic gate functions. Okay, then 0, 1, what happens? 0, 1, what happens? N1 is off.
0.
N2 is on. Correct? N2 is on, but not no use. Correct? Yes or no? N1, N2, if anyone is on, only one is on, Y cannot be connected to logic 0. Correct? Only when both N1 and N2 are in on condition, Y can be connected to logic 0. All of you getting? Yes or no?
Sir.
Getting this point, everyone?
Yes, sir.
Yes, sir.
Yes. Now, what is happening to the pull-up network? In pull-up network, P1 is
P1.
going to be in what? On condition, whereas P2 is going to be in off condition. But P1 being in on condition is more than sufficient to pass logic 1 to output Y. Output will be happily logic 1. Agree? Yes or no?
Yes, sir.
Okay, yes. Similarly, play for 1, 0 quickly now. So 1, 0 means A is 1. A is 1 means N mass 1 turns on, but B is equal to 0. N mass 2 turns off, but still Y cannot be connected to logic 0. So Y must be connected to logic 1. Who is offering that path means? So A is equal to 1. P1 will go off. B is equal to 0. P2 will turn on. Therefore, P2 will pass logic 1 to output Y. So it's 1. Agree? Easy?
Yes, sir.
So the beauty of digital logic is after the class, if you see only this slide, you won't understand. Because a lot of understanding is happening, okay, in the slide itself. Based on that only, I'm writing every row of our combinations, correct? Okay, so yes, listen carefully and understand things. 1 and 1. Both NMOS transistors will turn on because they are looking for active high. It is happening in A and B. Okay, so intentionally the two PMOS transistors goes off now. That means what?
Y equal to 0.
Yes.
0.
So there is no way for Y to be connected to what? Logic 1. Under this condition only, Y is connected to logic 0. So that means there is no conflict in any combination. That's how you need to connect or design your pull-up network and pull-down network. So very careful design of pull-down and pull-up always needed when you play with respect to the CMOS level. Getting everyone? So at a time, pull-down as well as pull-up, don't create a conflict of pulling them to logic 1 and pulling them to what? Logic 0. That means so like pull-up network placing 1 on output Y, pull-down network trying to place 0 on output Y is not happening. So if pull down Y is not pulled down to 0, it is always connected to the pulled up to the logic 1 only. So such a careful design is made. Hope you're getting, hope you're understanding this point. Is it clear?
Yes, sir.
So how to design such a thing means the moment you put NMOS switches in series, by default, the rule of thumb for PMOS, they have to be connected in parallel. Or if you put PMOS switches in parallel, your NMOS switches must be connected in series. Okay, so what are the PMOS switches? The two PMOS switches sensing A and B, they are connected in parallel means automatically the NMOS switches forming the pull down network should be connected in series. That's a logic we need to follow. Yes, there also there is a complementary. If pull down network switches are in series, pull up network switches must be in parallel. Then only this is possible. All of you getting this point? Getting?
Yes,
Yes,
sir.
sir.
Yes, that's a rule of thumb. If that is the case, you can think of another logic. So shall I put two PMOS switches in series and two NMOS switches in parallel? What will happen? We'll see. That is going to be the next logic function. First, let us conclude. So now we have a two CMOS, okay, digital logic circuit. Tell me what is the connection between Y, the output Y, and the inputs A and B. What digital logic function this is implementing?
NAND, sir.
What is Y? So the Y is equal to, yes, Y is equal to, Y goes to 0 only when? Y
Both
goes to
are
0 only when both are equal to 1.
1.
So therefore, Y is equal to A and B whole bar. So what is the logic implemented? This is CMOS NAND logic. This is CMOS implementation of what? NAND gate. CMOS NAND gate, you can say, okay? Instead of logic, happily you can call it as CMOS NAND gate. 1 minute, stay online. Okay, CMOS NAND gate. Last one is CMOS. Last one is CMOS.
Not gate.
NOT gate. Okay, so we have implemented NOT. What is the cost of NOT?
1 CMOS.
Cost of NAND.
2 CMOS.
2
2
CMOS.
CMOS.
And what is the symbol? This entire circuit is getting the symbol shortly like this. Okay, yes, that's a symbol of your NAND. So that is representing this whole circuit. Instead of weaving the whole circuit, we wanted to realize entire circuit like a simple gate. That's what the gate we call it as NAND gate. So simply implementing a function AB. So this is the whole circuit. You can take A and B. So you have to connect A to A. You have to connect B to B. Okay. So then you have to pull it out like this. Okay. You have to connect A to A. This is the actual setup. You have to connect A to A. Refer the dot connection. That's your signal A. That's how they will give. Okay. In the examination. And then they will connect these two. And then we'll connect it to B. Okay, don't get confused. Okay, that's how it will look like. Okay, so two inputs, one output, resembling a simple NAND. Easy, everyone? Easy, right? 1 minute, stay online. Hope it is clear, everyone. Yes.
Yes, sir. Yes, sir.
Yes, sir.
Okay, that's NAND logic. So we are making an important conclusion. Yes, parallelly we are getting the budget. How many transistors are needed to implement one? Not transistors means it's CMOS budget. Okay, or exactly speaking, two transistors. So one CMOS is two transistors, one PMOS, one NMOS. Okay, so you can multiply how many CMOS multiply by two. So many transistors we use for that implementation. Because in future we're going to build all the logic systems, digital logic system only by using this logic gates. Once you know the budget of a single logic gate, then by knowing how many such logic gates we are using, we can go for a similar budget in terms of CMOS. Instead of logic gate budget, you can go for CMOS budget. So what's the cost of my design in terms of number of CMOS transistors I demand to implement such a or realize such a digital logic design. Okay, so that's why implement everything only by using CMOS. So get that habit now itself. Okay, even if you go to that VLSI level, so that's how the digital system design will take you to that level only, VLSI level only. So in fact, that's habit of even in VLSI, you're going to play with the habit of CMOS only. So get that habit now itself. Okay. So that's why introducing the logic gates instead of directly asking, do you know the symbol of NOT? Do you know the symbol of NAND? Like that, I'm just introducing the implementation of every logic function so that you'll be very clear about how those gates are implemented or realized. Easy? Getting everyone?
Yes, sir.
Now you do the swapping. That means put the PMOS switches in series and put the NMOS switches in parallel. Tell me what that is going to implement. We'll see. Or one can begin the design like this. It's VDD. One can begin with a pull-up resistor. Then you can have two NMOS. I may give like this also. I'm showing only NMOS design, not involving any PMOS transistor. Like this also I can show certain design. Yes, you must be capable of getting the result. And this is the signal A, this is the signal B, and this is the signal Y. Tell me what is the digital logic implemented by using this NMOS only, no PMOS. It's not the CMOS implementation, it's a NMOS implementation of some logic function. Tell me what is a logic function implemented now. A, B, Y. That's easy. A and B are the inputs, Y is the output. Yes, A is equal to yes, combination 0, 0, 0, 1, 1, 0, 1, 1. Yes. Yes. 0, 0.
So for any of the inputs as one, we'll get a output as one, sir. So for the first scenario alone, like 0, 0 alone, we'll get the output as 0.
Check once. Magesh friend, check once. If you give 0, 0, let me have a copy of this.
0, 0, 0.
Okay, first case. I'll begin with the first case. I'm giving A is equal to 0, B is equal to 0. Yes. Both NMOS switches are in off condition. Correct?
Yes, sir.
Yes, sir.
Then Y is pulled up to?
1.
Yes, what is the current here? 0.
1.
0.
And what's a drop here? 0. What will be the Y level? VDD. What is that? Logic? 1.
1.
So yes, getting Mahesh friend?
Yes, sir.
Yes. Okay. Yes, you just complimented the result.
Yeah.
Okay.
Yeah.
Okay. Yes, that's a perception. That's a first logic. Then make it 0, 1. So next it is 0 and this is 1. Yes. Now this is off. Whereas this is in what? On condition. So this NMOS being an on condition, Y is pulled down to logic
0.
0. So Y is going to be logic 0. Easy? Akshaya, following?
Yes, sir.
Okay, yes. So we have a pull-up resistor. We have a pull-up resistor, not a switch, and we have pull-down network of switches. That's NMOS implementation of something. Okay. Yes, the logic idea we got it from this only. Okay, why can't I put the two NMOS in parallel? So I just wanted to give you NMOS digital logic instead of CMOS digital logic. Sometimes they may give like this. That's fine. Okay, you should be familiar with that. Okay, then this is 0 0 combination. This is 0 1 combination. Then let us go for 1 0 combination. 1 0. So I'm making this is 1. This is 0. That's easy now. 1 0 means yes, NMOS.
Zero.
This NMOS turns on and this goes off. Any one NMOS on enough to make y is equal to logic 0. So
Zero.
therefore 1 0 makes output logic 0. Yes, then the final both are in one condition. Okay, so any one NMOS is on, it's enough to make the output 0. That's a point. So then how to fill the table then? If anyone is on, anyone is 1, y will be equal to 0. Only when both are in off condition, y will be logic 1. So tell me what is the logic we are implementing now?
NOR.
No.
Exactly. That's your NMOS NOR logic. Okay. So one can build easily NMOS design. So once you comfortably make, yes, always begin with the NMOS design. Whatever the logic function you want to make, build it by using NMOS. Then replace this pull-up resistor by using PMOS switches. How to replace that? Yes, you know already well-built pull-down network. Just get the complement of pull-down as your pull-up. So here the pull-down switches are connected in parallel. You put the pull-up switches in series, then automatically that's realized. So now then you can go for a CMOS NOR logic. Okay, easy everyone? Easy?
Yes, sir.
Yes.
Then you make it. Yes, because CMOS may look little complex. That's why you make it by using NMOS. Then copy the NMOS pull down design for the pull up, but complement it. If they are parallel, make it series. Okay, if they are series, make it parallel. So that's a CMOS NOR logic. Yes. The top is VDD. First, go for your pull down network. Okay, so this is your output Y. So make your pull down network. This is the ground. So it's a pull down network. Two NMOS switches in what? Parallel. Yes, again, complete that. Okay, either you can directly connect them to ground or by habit, you can also tie them together and then you can connect it to the ground. That's fine. Okay. To make it fair, that's it. So this is the output Y. So when output will be pulled up to 0, pulled down to 0, this is A, this is B. If any one is 1, Y will be pulled down to logic 0. So we need to go for the complement of this. Then you have to put the two PMOS switches in series. Let me have some more space. Happy? But you need to confirm. Let us verify. Is it okay in all aspects or not? We need to verify this. Okay. Yes, let us have the table. A, B. So call them as P1, P2, N1, N2. So N1, N2, P1, P2, and your Y. Again, exhaust all the possible combinations 0, 0, 0, 1, 1, 0, and 1, 1, one by one. Yes, tell me what happens now. Verification of your design. 0, 0, both NMOS will be in off condition, but both PMOS are in on condition. Yes or no?
Yes,
These
sir.
are active high switches. These are active low switches. Yes. P1, P2 both are getting logic 0. So it's 1 and 1. So both are 1 means Y is connected to VDD. That is equal to what logic? 1. Agree?
1. Yes.
And what is happening interestingly here? Both NMOS 1 and NMOS 2 are in off condition. Then the moment you make this combination 0, 1 combination, then 0, 1 means NMOS 1 is still off, NMOS 2 goes on. Okay, whereas PMOS 1 is still on and PMOS 2 is off. Okay. Now, if any one of this PMOS is in off condition, VDD cannot be connected to Y. That's what the pull-up network is doing. And pull-down network says, if any one of the switches on, I will pull Y to logic 0. And pull-up says, only when both P1, P2 turns on, I will pull Y to logic 1. So when both will be turned 1, when both P1 and P2 will be turned 1, only for 0, 0 combination. Correct? All of you getting?
Yes, sir.
So that's only possibility where Y will be pulled to logic 1. Rest of the possibilities, pull down network is enabled, whereas pull up network is what? Disabled. So this is the only one combination enabling pull up network. Pull up network means completely the pull up network connects VDD to Y. There is logic 1 to Y. Rest of the combinations will never enable the pull up network. Always the pull down network is getting what? Enabled. So these three combinations will enable the pull down network. Means what? Pull down network enabled means pull down network is pulling the Y to logic 0. Okay, for this rest of the combinations. So need not to go through these things. Okay, you can check. Okay, 0, 0, 0, I can feed. Correct? Because anyone NMOS in on condition. Because B1 NMOS 2 is on, A1 NMOS 1 is on, both are 1. It is connected to logic 0 only. Correct? Easy? Yes.
Yes, sir.
What is the important point? When pull-up network is enabled, it must be disabled. Correct? When it is enabled, this must be disabled. Agree? All of you getting? When this is disabled, disable means not connected. Okay, two, it is not. The enable means Y, one is connected to Y. Disable means it is not connected. So disabled. So when it is enabled, this is disabled. When this is disabled, this is enabled. Agree? All of you getting? That's
sir.
how you have to design pull up and pull down network carefully. At a time, both should not be enabled, both should not be disabled. Okay, so that's a very careful design for pull up and pull down. So that's why I'm giving you the guideline how to build a CMOS NOR logic. Means first go for NMOS NOR logic, or you can also make it PMOS NOR logic, no problem. How to make a PMOS NOR logic? How to make a PMOS NOR logic? Anyone? Can you say how to make a PMOS NOR logic? If you want, yes, they may surprise you by giving PMOS NOR logic. So you got a logic now to play with. What is the logic? So a resistor in the pull up and NMOS switches in the pull down. So you see the CMOS design. So your pull down network is as it is, and pull up is replaced by your switches. Then what you can do is, if you want to make it PMOS, keep the pull up as it is, replace your pull down by a resistor. Easy. All of you getting?
Yes, sir.
Yes, do that. That's very easy. If you want to make a PMOS NOR logic, then have VDD, then connect the two PMOS switches in series. Once you have CMOS design, then you can understand, you can go for any other implementation also. Okay, so that's your output Y, that's your pull down resistor. So here you connect A, here you connect B. Now tell me, what is your PMOS NOR logic? Hope it is realizing the same. Now let me check with the table A, B and Y. Yes, now tell me 0, 0, 0, 1, 1, 0, 1, 1. Tell me what is happening to Y. Tell me when Y will be pulled up to logic 1.
When both are 0.
Yes, when both are 0. Rest of the condition, Y will be automatically
0.
0.
0. Yes, wonderful. Yes, see this. That's the beauty of your digital logic implementation. Logic functions only, logic gates only I'm talking about. Okay. This is the NOR logic. Okay. So this is what getting a symbol like this. Okay. A, B, and result is what? A or B, the whole bar. Agree? Easy, right? So hereafter you won't get surprised, even if it is NMOS design or PMOS design. Now you separately make NMOS design and separately make PMOS design, replace the two resistors. That's all. That is going to become a CMOS implementation. And you know what is your pull up? You know what is your pull down? Then club the two, result is your CMOS. Easy. Easy, everyone. Are you getting?
Yes, sir.
It's up to you. Okay, so you can realize first, if you feel CMOS is complicated, first separately make NMOS logic and then separately make PMOS logic and simply replace pull up by PMOS, replace pull down by NMOS. That's your CMOS logic function for the same logic function, whatever you are implementing.
Sir,
Yes.
sir, for PMOS logic, we should not connect PMOS in parallel, no, sir?
Yes, connect. Correct. Because I said already the guideline. What is that? In pull down network switches in parallel தானே?
Yes, sir.
அப்போ அதே லாஜிக் ஃபங்க்ஷன் தான் நீங்க இம்ப்ளிமெண்ட் பண்ண போறீங்க. அப்ப என்ன பண்ணணும்? புல் அப்ல you have to put the switches in series automatically. Complement to pull down. Complement to pull down na series na parallel na series. It's a logical complement தான் உங்களுக்கு. Getting
Okay, sir. Yes, sir.
Okay, yes. Yes, that's a rule we need to follow. Always the pull up network and pull down network are complement to each other. Pull up and pull down are complement to each other in all aspects. Pull down made up of NMOS. Complement of NMOS is what? PMOS only. So pull up made up of PMOS. Or pull up is made up of PMOS. What is complement of PMOS? NMOS only. So pull down is made up of NMOS. Correct? Getting Akshaya?
Yes, sir.
Okay, yes. So that complementary logic we need to follow for pull down as well as pull up. Okay, so yes, pull down and pull up are complementary logics with respect to switching logic theory, because one is in enable condition means another one must be in disable condition. So automatically when other goes to disable condition and the another one goes to the enable condition. So yes, complementary logic, that's how it has to be connected, so that there won't be any conflict that both pull up and pull down are in enable condition or both are in what? Disable condition. That situation should never arise. Okay, getting Akshaya?
Yes, sir.
So what are the logic functions we have implemented? We have implemented three basic logic functions, three important logic functions we have implemented. So one is NOT logic, another one is NAND logic, another one is what? NOR logic. Yes, what is the NOT logic? NOT is the entire CMOS circuit is any implementation either implemented by MOS transistors or implemented by BJTs. Finally, it is getting the symbol. This is CMOS implementation. So this cost as one CMOS. And NAND, that is getting this symbol, the entire circuit represented by the simplest symbol. Okay, yes, NAND logic. So here the signal is A, result is A bar. Here we have two signals, two inputs A and B. The result is A dot B whole bar. That's your NAND logic. Okay, so what is the cost of the design?
2 CMOS.
2 CMOS. Then we have built recently a NOR implementation. This is A and this is B. It is A or B, the whole bar. That's a NOR logic. Yes, what is the cost of the design?
2 CMOS.
2 CMOS.
Yes, by using 2 CMOS, you can implement either NAND or NOR. So later, why I'm talking about all these things means later, all your SOP designs are built purely by using NAND gates. All your POS designs later built by using only what? NOR logic gates. What is SOP? Sum of
Products.
POS, product of
Sum.
So whenever you go for POS implementation, always we are going to use NOR gates. Whenever we go for SOP implementation or realization, we have to use strictly the NAND logic functions. Then we'll see. Okay, so we'll talk about SOP. We'll introduce them in detail. Why we call it as SOP, why we call it as POS. So any SOP implementation demand only pure NAND solution. Any POS implementation demand pure NOR solution. So in digital logic design, any digital logic design is going to follow either a pure NAND solution. Instead of SOP, I can say pure NAND solution. That means entire setup is implemented only by using NAND logic gates. Our entire system is designed only by using only what? NOR logic. So there is NOR solution. So we are going for later, we want to implement any DLD. So any digital logic design, we're going to implement either purely by using NAND gates only or purely by using NOR gates only. Why? Because NAND and NOR are, yes, they are
Universal.
universal logic functions. Why they are called universal logic functions? This is a universal logic function. This is also known as universal logic function. Why we call them as universal logic functions? Yes, tell me. Universal means widely used logic functions. Why they are called universal logic functions?
It's actually easy to build an AND gate or a NOR gate with AND gate or OR gate with the NAND and NOR. So the
Yes.
combination of NAND and NOR will produce different types of logic gates.
Okay, so by using NAND alone, you can make NOT gate. NAND is already there. You can make AND gate. You can make OR gate. You can make even a NOR logic function. You can make an exclusive OR implementation. You can also make exclusive NOR. That means any digital logic function can be implemented by using only NAND or only by using NOR. Yes, any logic function can be implemented by using only NAND or only NOR. So we call them as universal logic gates. Understood, everyone? Everyone? All of you getting?
Yes, sir.
That's the reason we call them as universal logic gates. No other gates will have this designation. Okay, so only NAND and NOR are called as universal logic gates. That's an important point in digital logic. Okay, universal logic gates. So any logic gate or logic function can be implemented. Any function can be implemented only by using NAND, or any logic function can be implemented only by using NOR. So we call them as universal logic gates. So that's important. That's the reason first the focus is on implementing NOT and then NAND and then NOR. Okay, easy, right? Hope you understood the logic behind why we are focusing initially NAND and NOR instead of AND and OR. So can you tell me who is costly, AND or NAND? Anyone tell me who is costly, NAND or AND?
AND is costly.
Yes. Probably we remembered in reverse. How means, for example, how you will implement. I'm asking how you will implement NAND. I'm asking before knowing this. I'm asking how you will implement NAND means. Then your answer will be first I will take a AND gate and then we'll connect what one? NOT gate.
NOT gate.
Then, okay, then what is the cost of the design? Okay, this is how you feel like an AND gate is implemented, but actually how AND gate is implemented means because first what is getting implemented is not AND, only NAND is getting implemented by using 2 CMOS. Then after that, if you want to implement AND gate, first you need to have a NAND followed by a NOT, because AND is not implemented by using CMOS. NAND is implemented. So A dot B whole bar, this one is going to produce and pass this digital logic to the inverter gate by using one CMOS that will produce output A dot B. So therefore cost of AND, what is cost of AND?
3 CMOS.
Yes, that's it. That's it. That's the purpose of building everything now. Now, suppose if you do like this, tell me what is the cost of the design. I'm asking what is the cost of, cost of AND is 3 CMOS and cost of NOT is 1 CMOS. Suppose if you go by this design, tell me what is the cost of this?
4 CMOS.
Yes, which one is better? So this is what we perceived earlier. Okay, so what we are implementing is first NAND only, and is derived from NAND, and logic is derived from NAND. So therefore, and is costlier than NAND. Okay, getting everyone? And logic gate is derived from NAND. Easy. So NAND demands only 2 CMOS implementation, and demands 3 CMOS implementation because it demands additional inverter logic. Easy? Yes.
Yes, sir.
And same thing happens for your NOR also. Okay. So before we thought NOR means, okay, NOR gate. Okay, means we thought first we will take an OR gate and then we'll cascade to one NOT gate. And you know now, and this demands only what? 2 CMOS. But if you go for this design, yes, I want to make OR logic. Tell me, I want to make OR logic. Already shown AND logic. Okay, this is the OR logic and logic implementation, AND gate or AND logic gate implementation product, or a dot gate also we can say, that demands 3 CMOS. Similar to that, what is OR logic? What we have is first what? NOR only. Output of NOR A, B, A dot B, A or B, the whole bar is fed to. Fed to.
Not logic.
Not gate.
Yes, not gate. That's a practical CMOS implementation. So the result is going to be A or B. So this is demanding 1 CMOS and this is demanding what? 2 CMOS. So the cost is going to be what? R
3
logic
CMOS.
demands, yes, 3 CMOS. So cost of R is 3 CMOS. Cost of and also 3 CMOS. But suppose if you go by this, I'm implementing an NOR by using one OR gate and NOT gate, mean this is 1 CMOS and this is again 3 CMOS, and this implementation is costlier. How much?
4 CMOS.
I will ask you a simple question. What the cost of NOR logic means? You should not say 4. You have to say only what?
3.
You have to say only what? Cost
2
of
CMOS.
NOR. 2 CMOS only. Okay, they are cheaper. So NOT is cheaper. Okay, next cheaper is other than NOT. Okay, who is cheaper? NOT is not universal logic function. With NOT alone, you can't implement anything, everything. So you need NAND and NOR only. Okay, so NAND is universal, NOR is universal, but they are still cheaper. Okay, so don't compare NAND and NOR with NOT. Okay, NOT is the cheapest design, but we can't implement all the logic functions only by using NOT gates. So we demand actually a NAND logic and NOR logic to implement any function. Okay, so we call them universal logic functions due to that. Okay, fine, they are cheaper. They demand only 2 CMOS, but AND demands 3 CMOS, OR also demands 3 CMOS. Agree? Yes.
Yes, sir.
So now the list is okay. So apart from this, we have added 2 more. Okay, so 2 more logic functions. So now I'm not giving you the CMOS circuitry of AND and OR. I need not to give. You can imagine. Okay, I will simply say I have implemented one AND logic. Okay, then straight away I will say the cost of this AND is what? 3 CMOS. You know what is inside. Yes or no? That imagination already set. You have one NAND followed by one CMOS inverter. So that's your 3 CMOS AND logic. Okay, then similarly, we have also, you know how to implement one OR logic. That is also demands how many? 3 CMOS, correct? So how many logic functions implemented? Not. We know. Okay, what is the cost of NOT? We know the cost of NAND. We know the cost of NOR. We know the cost of AND. We know the cost of OR, correct? Agree? Yes.
Yes, sir.
They are all realized now. Okay. So we have realized only up to NOR. You know how to realize and you know how to realize OR now. Okay. So that feel like all are realized. Then what are all the remaining logic functions not yet realized? Not yet realized. we call a function known as exclusive OR, and another function exclusive NOR. Okay, yes, two more logic functions, important logic functions. You can call it as a gate, XOR gate and XNOR gate. Exclusive OR and exclusive NOR functions. Yes, these are the standard functions. We have the standard logic gate symbol. What is XOR symbol? XOR symbol is like your OR only, so that is getting the symbol. Correct? Yes. If I give A and B, what is the resultant? XOR function. XOR is getting the symbol A XOR B, exclusive OR B. What is it? A XOR B? What is A XOR B? That's my output Y. Why I'm calling it as A XOR B? What is that? We'll see. So I have A, I have B, and then first know the truth table, then we'll go for the implementation of this XOR logic as well. Okay, this is why. Yes, we're going to have again 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. What is XOR logic? We have covered NAND logic, NOR logic, AND logic, OR logic, everything we have covered. Yes. What is exclusive OR logic? Exclusive OR means, yes, what is that?
0, 0, 1, 1, 1, 1. Same element once.
That means when both the inputs are identical, output is logic 0. When both the inputs are identical, output is logic 0. When both the inputs are different, output is logic 1. That's what we call as exclusive OR function. It's all about how you perceive this. So when they are distinct, when the two inputs are distinct, result is 1. When they are identical, the result is 0. Opposite is your exclusive NOR function. What is XNOR function table then? XNOR function is going to have, again, the symbol is going to be put a bubble for the output, complement of this. So XNOR is going to get the symbol. Put a bubble. Okay. So then what is the result? It is A, it is B. Then you can say A XOR B, the whole bar we can say as your output, or you can also say A, the XNOR symbol is this. Okay. Getting everyone? Yes, this represents XOR operator. This represents XNOR operator. And this represents what? AND operator. This represents what? OR operator. Okay, yes, OR operator. Like that, this is the XOR representation. This is XNOR representation. Okay, we'll see what is XNOR. So this is exclusive OR table. What is XNOR table? Okay, XNOR is complement of this. Okay, so A, B, Y, you know. Okay, when they are identical, output is logic 1. When they are identical, output is logic complement of this table. That's your exclusive NOR function. Okay. Maybe you can also play with the Venn diagram. So there you can understand much better in aptitude. So let me straight away go with the logical conclusion. So when the two inputs are identical, output is 0 means that's exclusive OR function. When the two inputs are identical, output is 1 means that's exclusive NOR function. Then if they are different, output is going to be
0.
That's all, complement of it. Okay, so here Y is A XOR B, and here Y is A XOR B, the whole bar, or you can say A XNOR B like this. Yes, okay, so this is only a short representation of a logic function. So, or you can also say, I'm building a digital logic design. That's a combination logic design. Of course, we are getting into combination logic design. So CLD, I'm building a combination logic design because already I said what is combinational. Output is purely function of inputs. It is not function of the past outputs. So I'm building a combination logic design, taking the two inputs A and B and going to produce the output that Y is equal to A XOR B. Such a combination logic design only I'm calling it as exclusive OR function. Okay, what exactly this mean? So refer the table. Okay, so AB And this is y. Once again, 0, 0. Yes, tell me what is the resultant?
1,
0, 0. XOR
0,
1, 1, 0.
0,
So 0, 1, it is 1. 1,
1.
0, it is 1. Now tell me, what is y? Forget about this. Okay, what is y? From this, I'm asking. From the table, what is y? Give me a Boolean logic expression for y that is equivalent of a XOR b. When a is 0, b is 1, output is 1. When a is 1, b is 0, output is 1. Otherwise, it is 0. Shall I say like this, a bar dot b plus a dot b bar? Agree?
Yes, sir.
All of you getting?
Yes, sir. Yes, sir.
When a is 0, b is 1, output is 1. If not this combination. If not this combination, either this combination or this combination. Either this combination or this combination. So I'm using the operator or. So this or this, either 0, 1 combination or 1, 0 combination will make my output logic 1. That's what it means. Okay, so I'm getting a simple Boolean logic expression for y that itself is sum of products. Sum of
Products.
yes, what is sum of products? A bar dot b, this is a product term. We call it as a product term. This is another product term. So two product terms and operator I'm perceiving as a product, and the plus operator or operator I'm perceiving it as a sum. Getting everyone? I'm perceiving plus or operator as a sum. So it's sum of two product terms. So I'm calling it as y is an SOP expression. Y is a SOP Boolean expression. Getting everyone? All of you getting?
Yes, sir.
Yes, sir.
So we are about to implement exclusive OR function, not by using CMOS, because CMOS is only 3 implementation. We should know how to implement inverter, how to implement NAND, how to implement NOR. The rest is derived. And then you can straight away go for the budget. Now we are going to implement XOR. Already I have given some hint. So NAND is universal because any SOP function, any logic function can be implemented by using NAND. But interestingly, any SOP function can be easily implemented by using NAND. Don't make the cross logic. I want to implement SOP, but by using only NOR means it's a big challenge. But implementing SOP by using NAND is an easy challenge. That's what we're going to meet now. Okay, we'll see how we're going to implement this SOP function, which is an exclusive OR only by using NAND gates. We'll see that. Okay, so parallelly, I'm going to show how an SOP logic can be implemented only by using NAND gates. Okay. Easy, everyone? All of you getting?
Yes, sir.
So we are about to implement an exclusive OR logic function. So what is the function? This is called SOP function. This SOP y is equal to a bar b, a bar dot b if you want, or shortly you can write a bar b. It's anyway, it's a product, and then a b bar, correct? That's what we are about to implement. So this is what the Boolean logic function, we are calling it as exclusive OR function. Okay, we want to implement this. We are about to build a DLD. We call it as a combinational logic design. So how to realize an SOP function? How to realize an SOP function? Realize or implement using logic gates. Implement a SOP function. Sum of products function. Heading into logical design now. Exactly, that's a beginning point of digital logic design. SOP realization using logic gates. So first make this implementation using AOI. First find AOI implementation. First step 1. step 1 AOI implementation. Step 2 with some bridging steps. Step 2 will become pure NAND implementation. Yes, ultimately the goal is to make pure NAND implementation. Getting straight away to pure NAND solution is not the good choice. Okay, so better you make AOI implementation, then follow that implementation by using pure NAND implementation or solution. Implementation or solution. Ultimately, the goal is we want to implement an exclusive OR function using only NAND gates. What's the cost of an XOR, 2-input XOR? So what will be the cost of a 2-input XOR? I will say like this. It's A, it's B. This is your output Y. That Y is equal to A XOR B. What's the cost of a 2-input XOR? How many NAND gates are needed to implement one exclusive OR function? Maybe a 1 mark or 2 mark problem. They may give the circuit or they may make it in simple words. So we are going for a pure NAND solution. All of you getting? All of you getting this? Yes or no?
Yes, sir.
Then nobody is asking what is that AOI implementation. What is AOI? Getting? Yes or no? It's a short representation of AND or an inverter. All of you getting? So you take n number of AND gates, n number of OR gates, n number of inverter and implement this simple logic function. Implement this by using AND or inverter logic gates and modify such a AOI design into a pure NAND solution. Getting everyone? Yes.
Yes, sir.
This is how any SOP function can be implemented only by using NAND gates. We'll see. Okay, any other function. As of now, the challenge is we want to implement an exclusive OR function only by using NAND gates. So let us go through the first step. So let us implement XOR using suitable enough number of minimum number of AND gates, minimum number of OR gates, and minimum number of inverter gates. So now we are going for AOI implementation of XOR. So yes, AOI implementation. AOI solution shortly for XOR function. What is why I want to implement A dot B bar plus A bar dot B. Yes, now refer. You need signal A, you need signal B. You also need signal A bar, you also need signal B bar. Agree? Yes or no?
Yes, sir.
To get the complement of A, you need one NOT gate. To get the complement of B, you need another NOT gate. So that means first we need to use how many NOT gates? That's a budget. How many NOT gates? All of you getting?
Yes, sir.
We need minimum. We need minimum 2 NOT gates, correct? Yes or no?
Yes, sir.
So that all the signals are available. A is available, B is available, A bar is available, B bar is available. Sometimes designer will say, assume the complements of signals also available means then don't take this 2 NOT gates in the budget. If they say clearly complements of signals are not available, then NOT gates are taken into the budget calculation of how many gates are needed to implement it. They will say how many AND, how many OR, how many NOT. Okay, so then depending on what is given, consider NOT or don't consider NOT. Okay, so assuming complements of A and B are not available, complements of inputs are not available, so we need to complement them on our own to get the signals A bar and B bar. So A bar is ready, B bar is also ready. So first you need to make A dot B bar. That means what I can do, I can use one AND gate to get this product. Okay, so one will get A, another one will get the signal B bar. And what is the implementation of this AND?
A dot
A dot B bar. So first product is ready. So call it as a product 1. I'm going for the product 2. So what is the product 2? For product 2, I need to get products, we need AND gates. To get the products, we need AND gates. Okay. What is that second product?
A bar.
A bar dot B. So one of the inputs can be what? A bar. Another input should be B. Easy? Yes or no?
Yes, sir.
Yes, sir.
So then to get B bar, so then you can have a NOT. I'm showing the complete implementation. So this is B producing B bar, one NOT is used. And this is A bar. So I need one NOT. So let that is A bar. So the signal is A. Okay, so this is B. That's all. So you can connect B wherever you have. You can connect wherever you have A. That's all. So anyway, the overall DLD will have two inputs. Only A and B are the inputs. Then the product is available. This product is available. Then what you need to do? You need to do OR operation between them. So connect it to an OR gate. Easy? All of you getting? Yes.
Yes.
What is the output? What is the output? A dot B
Y.
bar or this product, then A bar dot B. Yes. So the resultant is our output signal Y, which is later shortly given as A XOR B is implemented. That's your AOI solution of exclusive OR function. Agree, everyone? Easy?
Yes, sir.
If you directly implement it by using AOI logic, tell me what is the cost of the solution in terms of CMOS. AOI is not an optimal solution. AOI is a beginning solution. It's a first, as a student, okay, you want to make it things as simple as possible, means you have the free hand to choose n number of gates, but ultimately the goal is to implement the logic function. Yes, you are given the free hand, you are free to choose n number of NOT gates, n number of AND gates, and n number of OR gates, because any logic function is going to involve products and sums only. So we have two products and this is your sum. So we call it a sum of products expression. This is your SOP expression. So whenever the expression looks like sum of products, I will shortly call it as SOP expression. Okay, so we are implementing such SOP expression, that is exclusive OR function. So tell me what will be the cost of this. I'm talking about CMOS cost. What will be the CMOS cost? If you are implementing, assuming you are implementing it using your CMOS logic gates, you know this is one
11.
CMOS, this is one CMOS, and this is how many? Three
3
CMOS, and this is three
3
CMOS, and this also
3
three CMOS. Then what is the budget? The
11.
AOI solution has a budget of 11 CMOS. So if someone asks you what is the number of CMOS transistors needed to make an exclusive OR function, means don't say it's 11 CMOS. Can I say 11 CMOS? It is not an optimal solution. It's a first step solution. We'll try to optimize it. All of you getting? All of you getting this point?
Yes, sir.
Then we'll see how to optimize it. Okay, let me check the timing as well. Okay, so let me take a few more minutes. Refer your AOI solution. Let me refer this way. This is A, this is going to be A bar, and this is B, and this is going to be B bar. Okay, so then, so the signal has to be B, you have to tie it to the B, and the signal has to be what? A, correct? This product is
A bar,
A bar
dot
dot
B.
B. This product is A dot B bar. That's all. Okay. So I see only the two inputs, A and B are the inputs to the digital logic design. So A can be connected here, and B can be connected here. That's all. Refer the dot connection. So overall, I have only two inputs, A and B, making the wiring accordingly. Okay, so now let me keep this as a copy. We'll do the editing. Yes, what is the connection you need to offer? If I give such a connection, what you will do? You will connect this wire, a wire here, and then a wire here. Then the result is going to be the desired Y, that is A XOR B, correct? Yes, everyone? Which
Yes.
looks like 11 CMOS budget, correct?
Yes.
Okay, instead of doing this, how to convert this AOI solution into pure NAND solution, we'll see. So I need to convert my AOI solution into pure NAND solution. You want to make it pure NAND solution. That means my circuit, digital logic circuit or design should use only NAND gates. So how to make it means connect two buffers, two NOT gates here, not buffers, two NOT gates here. Connect two NOT gates here. Tell me whether I am changing anything now. The signal is still A bar dot B only. The signal is still A dot B bar only because two NOT in cascade result is what? No inversion really, correct? No complements, correct?
Yes, sir.
Yes, sir.
Okay, so what is the benefit we are going to get out of this means I know this is going to be a NAND. Yes or no?
Yes, sir.
Getting Shweta?
Yes, sir.
And this is also going to be a NAND.
And
That's how one can convert an AOI solution into pure NAND solution. And how about this setup? I'm giving this. Okay, I'm giving separately this. Can you tell me what logic function is getting implemented by this setup? Tell me what logic function this is implementing. Say, for example, the two signals are X and Y. And this is signal X and this is signal Y. Tell me what is the signal? Complement of X or X bar? Complement of Y, Y bar. Tell me what is coming out?
X,
X bar plus Y
X
bar.
bar or Y bar. What is X bar or Y bar as per principle of De Morgan's?
X dot
X
Y.
dot Y the whole bar.
What is this fundamentally?
NAND.
NAND gate.
Excellent. That's a point. Okay, so rest is also another NAND. Getting everyone? That's what I want to prove. This is X dot Y whole bar. Okay. You see everyone? So this is pure NAND. This is pure NAND. This is pure NAND. And I have to implement only the NOT gates by using NAND. That's very easy. How to implement NAND by using, how to implement NOT by using NAND means. So this NAND NOT can be implemented by using one NAND like this. I'm implementing an NOT using NAND. Okay, see, I'm giving B. Tell me what is the signal coming out.
B bar.
So this is B. This is B. So as per the logic of NAND, it is B dot B, the whole bar. Yes or no? Yes or no?
Yes, sir.
What is B dot B fundamentally? If B is 0, 0 into 0, 0 dot 0, 0 and 0 is 0 and 0 is 0,
0.
0 and 1 is 0, 1
Zero.
and 0 is 0,
Zero.
1 and 1 is
1.
1, correct? But in this case, whatever
Whole
the
bar.
B takes, another B also going to take the same logic. That means we are going to have only these combinations, correct? Yes or no?
Yes.
Yes, sir.
So B dot B, if B is 0, result is 0. If B is 1, result is 1. So therefore, the result is B itself. Agree? Getting
Yes.
everyone? 0.0 is 0, 1.1 is 1. So that means it is going to have only this two combinations of your AND logic. Okay, so therefore I can say B dot B equal to B means result is what? Result is what? Complement of
B.
complement of B. That means similarly, this I can implement by using another NAND. So this is one NAND. Yes, now tell me what is the cost of the solution? How many NANDs you need?
5.
6.
Actually, implementing a not using NAND is costly, correct? Yes or no? What is the cost of NOT? Only one CMOS. What is the cost of NAND?
2
Two CMOS. That's what I'm saying. Implementing a not using NAND is costly, correct? But still, what is the solution we are looking for? Pure NAND solution. For the sake of, I want to implement everything only by using pure NAND solution. Why? For example, if you're going to the laboratory, digital circuit laboratory or digital electronics laboratory, when you're going to demand one NAND logic gate, it is available only as an IC. That NAND IC is going to have 4 NAND logic functions, correct? Yes or no?
Yes, sir.
Suppose if you are implementing this exclusive OR by using AOI, you have to demand first AND IC, you have to demand RIC, you have to demand inverter IC as well. So you will be using 3 ICs to make that logic function, correct? Even in laboratory, you'll be demanding 3 ICs. Suppose if you are implementing only by using pure NAND, one NAND IC will have 4 NAND logic gates. So if possible, try to implement XOR by using only that 4 NAND gates, which is available in single IC. If not possible, demand one more NAND IC. Even with respect to demanding of IC, the design cost is less only. Yes or no? Because it is going to demand how many NANDs? How many NANDs it demands? All of you.
5 NANDs.
5 NANDs only. So one NAND IC will have 4 NANDs. The demand 2 NAND ICs complete your design. So because it is going to be a pure NAND solution, even with respect to demand of ICs also, it's a minimal cost only. But anyway, we'll go with the budget of CMOS. How many NAND gates we are using now? How many NAND gates we are using now? Total?
5.
Okay, then the implementation will look like this. So with that, let me conclude the day. So when you are not speaking, keep the mic in muted condition so that the recording won't have any additional noise. Okay, so we'll go for the implementation. So we have a pure NAND solution of this exclusive OR function. They may give something like this. They will give you the surprise by giving pure NAND solution. Yes, it takes time to understand what is given. It's a pure NAND solution. Now we are going to play with the Boolean logic while verifying this. Whether it is working fine or not, we have to verify. That's a pure NAND. The circuit is consisting of only NAND gates, nothing else. Okay, this is the input A, this is the input B, and this is the input B, and this is the input A. That's all. Maybe given the connection. Okay, this is your B signal. Yes. Okay. So we have only 2 signals, A and B, for the entire design. So this is your DLD, combinational logic design inside the box. Our focus is what is the output, what is the input. Inputs are A and B, only one output, that is Y. Okay, so the goal is to find Y. Yes, that's implementation. Okay, so the cost of this implementation is 5 NAND gates. What is the cost of each NAND in terms of CMOS?
2, sir.
2 CMOS.
Even with respect to that, what is the budget?
10.
10 CMOS. Minimal? At least 1 CMOS less, correct? Yes or no?
Yes, sir.
So NAND solution is at least 1 CMOS better than your AOI implementation. Okay, so if you go by AOI, it is in fact even more costlier if you go for the laboratory implementation, because you'll be demanding AND ICs, you'll be demanding NOT IC. Okay, one AND IC is enough, one NOT IC is enough, and one OR IC will be demanding. That is a costly implementation of this exclusive OR function. Okay, the intelligent student will demand only two NAND ICs and implement the function XR. Okay, fine. Then we need to verify this. So let me keep this as it is. We'll do a small verification. With that, we'll conclude the day. Yes, can anyone verify? Hope it is realizing the function as we expected. Yes, first time you're going to play with the Boolean logic now. And this is the signal A. What is the signal coming out? A dot A whole bar, A bar, we know that. And this is a signal B. It is B, it is B. What is the signal coming out? B bar. So what is the signal coming here? Tell me now. What is the signal coming here? A bar dot B, the whole bar is coming out. Agree? Yes or no?
Yes, sir.
What is the signal coming here? A dot B bar whole bar is coming now. It's complicated verification. Okay, complex verification. So let me call this a signal X, and this, okay, X and Y are already used. Y is used. Okay, let me go for another signal. Yes, let me assume it is a signal P, and this is a Q. Okay, so what is Y then in terms of P and Q? It's P dot Q, the whole bar. Agree? Yes or no?
Yes, sir.
Then Y is equal to, substitute your P. What is P? P is the signal and Q is the signal. Then what are you going to get? It is going to be A bar dot B, the whole bar. That's your P signal. Dot, what is the Q signal? A dot B bar. P and Q are just assignment so that I can make the Y's a simple expression. Now let me expand things. Okay, A dot B bar, whole bar. Then we have whole bar. Agree? Agree?
Yes, sir.
Love you getting?
Yes, sir.
Then recently, okay, we had a logic. Okay, what is the logic we had? So we know X bar or Y bar as per the principle of De Morgan's is equal to X dot Y whole bar. As per the principle of De Morgan's, we know X dot Y whole bar is equal to X bar or Y bar. Correct? Yes? Yes or no?
Yes, sir.
By using this identity, can I write Y is equal to A bar dot B, the whole bar, one more bar, and this and becomes R.
Yes.
Then A dot B bar bar bar. Agree?
Yes,
It is,
sir.
I'm writing it is like P bar R Q bar. Happy? Yes or no?
Yes, sir.
What is P? This is P. What is Q? This is Q. Agree, everyone? Getting all of you.
Yes, sir.
What is double complement of a signal? I have X double bar. What is that?
It's the original signal.
X.
X itself. Correct? X double bar is X itself means that means this double bar will get cancelled. But again, Y is equal to A bar dot B plus A dot B bar. That's a desired. That's a desired
XOR. Yes.
XOR function. Getting everyone? Getting?
Yes, sir.
Now you started playing in the Boolean way. This is how we need to reduce a Boolean expression. So it may look complex, but still we can reduce in the Boolean way. So here to reduce it, we are using the De Morgan's principle. Okay, so where we had only two variables, now we are having more than that. Okay, so that's a way, but this is not, this is only a 10 CMOS implementation. So in the next class, you try to optimize it further. Formally, you can't optimize. Formally, you can't optimize. Okay, further. Okay. So now I'll give you one circuit consisting of only NAND gates as an example. You tell me what logic function it is implementing. Take it as an example. You give me the solution tomorrow. Okay, so I'm using pure NAND solution. Some function I'm implementing. You tell me what is the function implemented. It's fully a function of NAND gates only. You can give me the answer tomorrow. Okay. A and B or X and Y. Okay. For a change. Another NAND. Then one more NAND. That is called Z. So find out what is your Boolean expression for Z. That's example. Just take the snapshot and try. Anyway, we'll share the PDF of the slide soon. Okay. Hope you can try. Similar to the last problem.
Yes, sir.
Okay. Yes, that's a challenge. Meet this challenge. We'll discuss about this tomorrow. Okay. So with this, let me conclude the session. So any doubts, you are free to ask. Yes, Akshaya, any doubts? Sweta?
No, sir.
No, sir.
Yes, you're Priya following, right?
Yes, sir.
Fine then. Okay, so yes, we are already into the core of digital electronics. Okay, we started making SOP implementations already. Okay, in the name of exclusive OR function. So started giving you the fundamentals of AOI implementation as well as pure NAND solution. Similarly, we'll take a POS expression. Okay, so tomorrow, and then we'll see how to make it pure NOR solution. Yes, you should know as a digital designer, as a front-end digital designer, always you should know how to implement an SOP function, how to implement a POS function. Then we'll get into the applications later. Okay. Now itself we are in an application that's exclusive OR implementation. Itself is an application. Okay. Fine. Thank you, everyone. We'll meet tomorrow. Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.